Delighted to be here to help celebrate Harold's 70th birthday and to celebrate the flowering of random matrix theory to which he has contributed so much. I have in my files a collection of wonderful handwritten letters that Harold wrote to me about 10 years ago when he and Craig Tracy were embarked on their grand tour of Fredholm determinants and Painlevé transcendence. The letters are full of enthusiasm and full of equations. Here is a man who is in love with mathematics. As we are gathered here to do him honor, we can say about Harold what the inscription in St. Paul's Cathedral in London says about Christopher Wren. Si monumentum quaeris circumscipe. If you're looking for his monument, look around. So I'm talking today to a group of experts, but I'm no longer an expert. I worked vigorously on random matrix theory for about 10 years, roughly from 1962 to 1972, mostly in collaboration with Madan Lal Mehta, sorry he's not here, and then went on to other things. Any expert knowledge I may have possessed is now 30 years out of date. I've only a very superficial knowledge of the beautiful things you people have been doing for the last 30 years. It would be absurd for me to try to talk about your recent work and painful for you to listen. The only subject I can talk about with authority is ancient history, so I'll talk about that. I'll try to pick out aspects of ancient history that have not been published and are not well known. Some of the old problems that we used to worry about might be worth revisiting with the more modern tools that are now available. Random matrix theory was invented by Eugene Wigner in 1951 as a branch of nuclear physics. In those days, nuclear physics was a fashionable subject for leading physicists to work in. Now, nuclear physics has been out of fashion for a long time, and the younger members of the audience probably never imagined that nuclear physics could have any connection with interesting mathematics. In the 1960s, when Mehta and I were working on random matrices, the connection with nuclear physics was always in our minds. The Wigner random matrix model was intended to be a model for the Hamiltonian of a heavy nucleus containing a large number of protons and neutrons with strong interactions. For such a nucleus, the standard models of nuclear physics gave a reasonably accurate picture of the ground state and the first few excited states. I might just put on another view graph as we go along. So these are just references that might as well have on the record. The low-lying states are simple enough to be described by a dynamical model with a few suitably chosen quantum numbers. But when you're looking at the highly excited states that are formed when slow neutrons are captured by heavy nuclei, there's no hope of describing them individually by a dynamical model. For example, when slow neutrons are captured in uranium-238, the common isotope of uranium, you see resonances at the energies of excited states of the unstable nucleus uranium-239. The binding energy of the neutron is about 4 million volts, and the spacings between the observed excited states are around 10 volts. That means there are about 400,000 states between the ground state of uranium-239 and these excited states that are observed close to the neutron binding energy. So Wigner said it makes no sense to try to write down a Hamiltonian or to solve the Schrödinger equation for the highly excited states. So let's go to the opposite extreme and assume we know nothing at all about the Hamiltonian. Let's assume the Hamiltonian for uranium-239 is a matrix chosen at random from a suitable ensemble. Wigner chose the ensemble to be the set of all real symmetric n by n matrices with each matrix element an independent Gaussian random variable. The assumption that a state of the nucleus is an eigenfunction of such a random matrix tells us nothing about the properties of the individual states. But, as Wigner discovered, the assumption that a set of states are eigenfunctions of the same random matrix tells us a great deal about the statistical properties of the eigenvalues. The eigenvalues of a random matrix are not randomly distributed, but show strong correlations which can be calculated precisely. The distribution of spacings between nearest neighbor eigenvalues was calculated analytically by Michel Gaudin in 1961 and was found to differ very little from the empirical formula conjectured by Wigner. This was a beautiful piece of analysis. It was Gaudin who first understood the intimate connection between random matrices and Fredholm determinants. When I began working on random matrices in 1962, the motivation was still, as it had been for Wigner, to use the random matrix model to interpret experiments in nuclear physics. The experiments in the 1960s were done at the Nevis cyclotron of Columbia University by Jim Rainwater. Rainwater had developed the art of time-of-flight neutron spectroscopy to a high degree of refinement. The trick was to use a rapidly rotating shutter to let out a short pulse of slow neutrons with a wide range of energies, then let them travel a long distance before measuring their absorption in uranium or some other absorbing material. The time of flight of each neutron was inversely proportional to the square root of the energy. The peaks of absorption as a function of time gave an accurate measurement of the neutron capture levels as a function of energy. Rainwater maintained measured long series of capture levels in uranium, thorium, and other heavy elements. The most interesting for testing the random matrix model turned out to be erbium-166. The compound nucleus, erbium-167, happens to have the longest series of levels within the range that Rainwater could measure accurately. I worked with Rainwater and a graduate student called Henry Kamada analyzing the experiments. Kamada is now a professor at Penn State. Rainwater, after sharing a Nobel Prize with Orr Bohr and Ben Mottelson for discovering that many heavy nuclei are non-spherical and have states characterized by rotational quantum numbers, died in 1986. So section 2, cryptography and error-correcting codes. When we analyzed the Columbia experiments using random matrix theory, we were doing a kind of cryptography. The sequence of observed energy levels can be considered as a secret message. The nucleus is telling us something about itself, and the energy levels are the channel it's using for the communication. Our job as cryptographers is to extract all the information we can from the encrypted message. If the levels were randomly distributed and uncorrelated, the channel would be 100% efficient and would carry the maximum amount of information without redundancy. But the eigenvalues of a random matrix are strongly correlated, so they carry less information than a random sequence. The energy level channel is redundant, and the redundancy causes a loss of information. If we could measure the loss of information, we might learn something about the nature of the channel. To calculate the loss of information, we introduced another physical model which we called the Coulomb gas model. The Coulomb gas model is a set of equal point charges moving on a line, each pair of charges repelling each other with a force inversely proportional to the distance. It turns out that the statistical behavior of the charges in the Coulomb gas is mathematically identical to the statistical behavior of eigenvalues of a random matrix. And the loss of information due to redundancy in the energy level channel is exactly equal to the negative entropy of the Coulomb gas. The principle of equivalence of entropy and information, first discovered by Leo Szilard in 1928, says that information can be converted into negative entropy at a fixed rate. We avoid the discussion of the fixed rate by measuring entropy in information bits. The one-dimensional Coulomb gas belongs to the class of exactly integrable many-body systems, so the entropy can be calculated exactly. The result which we calculated for the entropy was up here, this first equation, 1 over 2 log 2, 1 minus Euler's constant gamma minus log pi times the number of levels. So it's just about minus 1/2 of a bit per level. The result was mathematically elegant, but practically disappointing. 1/2 of a bit is a miserably small amount of information. We wanted to verify whether this result is actually true for the energy levels measured by rainwater. We collected all the series of energy levels measured in various elements up to that time. Given a finite sequence of levels, it should be possible to calculate the entropy and compare the result with the theoretical value. But the calculations turned out to be frustrating. Different level series from different elements gave values for the entropy that were widely scattered. Most of the level series were too short to be useful. The longest series were thorium-232 with 101 levels, uranium-238 with 96, and erbium-166 with 82 levels. In spite of rainwater's heroic efforts, the total number of levels that was measured in all the experiments was only about 2,500. The wide scatter of the calculated entropies was probably due to the presence of missed or spurious levels. In a finite level series, 1 or 2 missed or spurious levels could make a big difference to the entropy, producing a noise signal that drowned out the theoretical 1/2 bit of entropy that we were trying to measure. So, having failed to verify the connection between random matrix theory and the nuclear data, we decided to follow a different approach. The main trouble with the data was that it was probably corrupted with missing and spurious levels. The visibility of a level depended on the strength of the neutron absorption. Since the levels were of widely different strengths, there was always a chance that a very weak level could be missed. There was also a chance that a weak level arising from some state with higher angular momentum would be detected and included in the series. The random matrix model was only supposed to apply to a series of levels with the same angular momentum, and states of higher angular momentum were supposed to be too weak to be detected. But we had to expect that a small percentage of genuine levels would be missed, and a small percentage of spurious levels would be included. Since, according to the theory, the level series was a redundant channel of information, it should be possible to find an error-correcting code that would automatically correct the data. In principle, according to Shannon's theory of error-correcting codes, so long as the information loss rate due to errors is smaller than the redundancy of the channel, an error-correcting code should exist that converts corrupted data into uncorrupted data. Applied to the nuclear level data, the code should automatically eliminate spurious levels and restore missed levels. This was a grand dream, a dream that by creative use of pure mathematics, we could clean up the messy results of nuclear experiments. It would be a great triumph for mathematics if an error-correcting code could correct nature's mistakes as well as our own. We worked hard to find an effective error-correcting code, but we never found one that fulfilled our dreams. The best we could do was to find an algorithm that could identify with reasonable probability a single missed or spurious level in a long series of otherwise correct levels. The algorithm could correct at most one error at a time. It was based on an optimized weight function. Here's the weight function, f of x. X is horizontal, f is vertical. No, other way around. X is vertical, f is horizontal. So there's the definition. It's just an elementary function. Essentially, it's a logarithm close to the x equals 0, and then it turns over into a sort of semicircular law at the extremes. And it's 0 outside this interval from +1 to -1. So given a series of levels Ej and a particular level Ei that you're testing, So then you choose an interval and choose an interval L over which you're doing the testing, and then you simply sum this weight function f over the different levels, and that's then a diagnostic for the level at the position I. So this is a score to test the validity of the level E sub I. It's a sum over all the levels Ej other than Ei between Ei minus L and Ei plus L. So it just goes over the levels in the interval. The interval L is chosen to be, for convenience, about 10 times the level spacing, which is capital D. If you're given an observed set of levels Ei, you test them by calculating the scores f sub I. If the levels are an error-free sequence of eigenvalues of a random matrix, all the f's should have the same expected value. Here it is, equation 5, n minus delta. So n is the average value. It's the average of f over the interval, and delta is the correction due to the level repulsion. So if the levels are an error-free sequence, all the fi will have the same expected value, n minus delta, where delta is then just essentially logarithm of n, logarithm of the number of levels in the interval, and n is just the pi L over d, which is essentially the area of the curve divided by the width. It's the average of f. And the values are then scattered with a standard deviation, which is the square root of log n. So you're working on the difference between log n and the square root of log n, which is, of course, is not a very big difference, since the n is not a large number. These level series are just miserably short. And so the largest value you can use for n is about 30, and the logarithm is 2 or 3. So the difference between n and square root log n and square root of log n is only about a factor of 2 at the best. If the level is spurious, the score just has the expectation value n. So you're looking for the difference between n and n minus delta with a statistical scatter, which is roughly square root of delta. So if the level is spurious, the score has expectation value n, and the scores of neighboring levels will also be raised above the expected value. If a level ek is missing, the scores of neighboring levels will be lowered, below the expected value. So the next picture shows some actual experimental data, which is probably the only experimental data you'll see this week, so you might as well take a look at it. As you see, it's miserably bad. So these are the scores calculated by Henry Kamada for the 96 measured levels of uranium-238. So you see that this vertical line here is the expected value for a good level. The scores are going horizontally. Spurious levels should be on the right-hand line, and missing levels should be on the left-hand vertical line. And the dotted lines are the standard deviation. So you see what's really happening. The deviations of the scores from the expected levels are so large that they cannot be explained by a few missing or spurious levels. The results are just totally horrible for the theory. In this case, the error-correcting algorithm has failed completely. So most of the data was like that. And here's the best we had, which is our favorite nucleus, erbium-166, the only nucleus for which the algorithm works reasonably well. Here the scores cluster around the expected value with the expected scatter, except for the deviation around level 60, around here, which could be explained as the effect of one or two spurious levels. But even in this most successful case, the algorithm is not precise enough to identify the spurious levels and correct the errors. If this attempt to construct an error-correcting code using random matrix theory had succeeded, we would have published the results long ago, and I would not be talking about it today. I decided to talk about it just because it failed. Because it failed, we abandoned it, and nobody has tried to do anything with it for 30 years. The reason it failed was that the nuclear level data was qualitatively and quantitatively insufficient. We had too few levels and too many errors, so that an error-correcting code had no chance. As a contribution to nuclear physics, our work was worthless. I decided to talk about it because I still think it is an interesting mathematical problem. Now, 30 years later, I'm no longer interested in the nuclear levels. I'm interested in the general question whether error-correcting codes for random matrix eigenvalues are in principle possible. I'd like to know how to construct an efficient code and how high an error rate it could in principle correct. These problems are unsolved, and that's why I talk about them today and recommend them to your attention. I suspect they might lead you to some interesting mathematics. So that's the end of the first subject, more or less. In the theory of random matrices, there are three types of matrix ensemble, which we call orthogonal, unitary, and symplectic. The corresponding Coulomb gas models have three different temperatures. The orthogonal model has temperature 1, the unitary model has temperature 1/2, the symplectic model has temperature 1/4. In nuclear physics, because the nuclear Hamiltonian has rotational symmetry, only the orthogonal ensemble is relevant. That is unfortunate, because the orthogonal ensemble has the weakest repulsion between neighboring levels and the lowest redundancy of the three types of ensemble. The main reason why our error-correcting scheme failed was the low redundancy of the information channel in the orthogonal case, calculated to be only 0.521 bits per level. The higher the temperature, the weaker the repulsion between levels, and the smaller the negative entropy, and the lower the redundancy. The unitary ensemble has a stronger repulsion of levels and a substantially higher redundancy, calculated to be just gamma over log 2, that's equation 7, or 0.83 bits per level. The symplectic ensemble is even better, with a redundancy of 1.223 bits per level, more than twice the redundancy of the orthogonal ensemble. If we are studying the possibility of error-correcting codes as a problem of pure mathematics, not as a problem of nuclear physics, we might as well study the unitary or symplectic eigenvalue series for which the redundancies are higher and the chances of successful error correction are more favorable. We will encounter the unitary ensemble again in a little while when I discuss the zeta function. So, second topic, quasicrystals. I'm presenting a challenge to young mathematicians to study quasicrystals and use them to prove the Riemann hypothesis. Those of you who are experts in number theory might consider the challenge frivolous. Those who are not experts may consider it unintelligible. Nevertheless, I'm putting it forward for your consideration. You should always be guided by the wisdom of the physicist Leo Szilard, who discovered the connection between redundancy and entropy. He wrote down his own 10 commandments to stand beside those of Moses. Szilard's second commandment says, "Let your acts be directed toward a worthy goal, but do not ask if they will reach it. They are to be models and examples, not means to an end." So the Riemann hypothesis is certainly a worthy goal, and it's not for us to ask whether we can reach it. I'll give you some hints describing how it might be achieved. Here I'll be giving voice to the mathematician that I was 50 years ago before I became a physicist. There were until recently two supreme unsolved problems in the world of pure mathematics, Fermat's last theorem and the Riemann hypothesis. Now that my Princeton colleague Andrew Wiles polished off the Fermat theorem, only the Riemann hypothesis remains. The Riemann hypothesis says that the Riemann Zeta-Function has all its complex zeros upon a certain line. The Zeta-Function stands at a junction where paths lead in many directions. Like every serious student of pure mathematics, when I was young, I had dreams of proving the Riemann hypothesis. I had some vague ideas that I thought might lead to a proof, but I never pursued them. In recent years, after the discovery of quasicrystals, my ideas became a little less vague. I offer them here for the consideration of any young mathematician who would like to have a Fields Medal. The fact that the Zeta-Function zeros have something to do with random matrices was discovered 30 years ago by Hugh Montgomery. Montgomery was studying the pair correlation function of the Zeta-Function zeros. He assumed the Riemann hypothesis to be true, so that all the zeros are on the critical line, the non-trivial ones. The pair correlation function P of x is the probability density for finding two zeros, not necessarily nearest neighbors, with imaginary parts differing by x times d, where d is the average level spacing. Montgomery conjectured on the basis of a non-rigorous calculation that P of x should be an elementary function. Here it is, equation 9, just 1 minus sine pi x over pi x squared. He was able to prove only a weaker statement that the Fourier transform of that equation holds for all frequencies not greater than 1. But nobody doubts that that equation is true. Andrew Odlyzko computed 8 million zeros near to zero number 10 to the 20th and computed their pair correlation numerically. The results are shown together with Montgomery's conjecture in the picture here. So there's Montgomery's theoretical curve and Odlyzko's computation of the actual level differences. And you see the agreement is perfect. You can even see the third wiggle around x equals 3 in the numerical data. That reminds me of the third wiggle in the spectrum of the microwave background radiation anisotropy that was recently measured by heroic efforts of microwave radio astronomers, which provided the conclusive piece of evidence that we live in a flat accelerating universe. If you can see 3 wiggles in the right places, then you believe the results. So there are the 3 wiggles in this case. So we believe that that equation, 1 minus sine pi x over pi x squared, is the correct pair correlation function for Zeta-Function zeros. Now comes the surprise. That equation is also the exact pair correlation function for the unitary ensemble of random matrices, defined as the ensemble of complex Hermitian n by n matrices with real and imaginary parts of each element independent random variables. As you can see in the picture, the unitary ensemble has a strong repulsion between pairs of levels. The density becomes very small when they come close together. The repulsion is twice as strong as in the unitary ensemble as it was in the orthogonal ensemble that we used for heavy nuclei. The wiggles demonstrate that the Zeta-Function zeros have some sort of vestigial long-range order, a memory trace of a regular crystalline structure which makes differences between zeros prefer to be integer multiples of the average spacing. This long-range order is a well-known feature of random matrix eigenvalues. So we have a striking but not yet understood connection between the Zeta-Function and random matrices. The Zeta-Function zeros behave as if they were the eigenvalues of a random Hermitian matrix. This immediately suggests the question whether we could pick out of the unitary ensemble the particular one Hermitian matrix that has the zeta function zeros as its eigenvalues. If we could pick out the right matrix, we would know that all its eigenvalues are real, and we would know that all the zeta function zeros are on the critical line. Peter Sarnak has extended Montgomery's work and found that not only the pair correlation function, but all the many-level correlation functions of the zeta function zeros agree with those of the unitary random matrix ensemble. The agreement of the many-level correlation functions is still a conjecture, but nobody doubts that it's true. Sarnak has proved that the Fourier transforms of the many-level correlation functions are equal over a wide range of frequencies, just as Montgomery did for the two-level correlation. Since Peter Sarnak will be talking here tomorrow and knows 20 times as much about the subject as I do, I won't say any more about it today. There's an excellent and readable account of this story in a lecture by Andrew Granville, published in the MSRI newsletter Emissary in spring 2002, which probably many of you have read. And if you haven't, I recommend it. Now I jump from the Riemann hypothesis to quasicrystals. Quasicrystals were one of the great unexpected discoveries of recent years. They were discovered in two ways: as real physical objects formed when alloys of aluminum and manganese are solidified rapidly from the molten state, and as abstract mathematical structures in Euclidean geometry. They were unexpected both in physics and in mathematics. I'm here discussing only their mathematical properties. Quasicrystals exist in spaces of 1, 2, or 3 dimensions. From the point of view of physics, the three-dimensional quasicrystals are the most interesting, since they inhabit our three-dimensional world and can be studied experimentally. From the point of view of a mathematician, one-dimensional quasicrystals are much more interesting than two-dimensional ones because they exist in far greater variety, and the two-dimensional ones are more interesting than three-dimensional ones for the same reason. The official mathematical definition of a quasicrystal is as follows. Well, I don't know whether I have to go through all this, but I'll put it on the board at least. So a Delaunay set is a set of points in Rn with positive numbers little r and big R, such that no sphere of radius little r contains more than 1 point, and every sphere of radius big R contains at least 1 point of the set. So it means that it's a set which is more or less evenly spaced over Euclidean space, nowhere too dense and nowhere too sparse. A quasicrystal, then, is an aperiodic Delaunay set whose Fourier transform contains a countably infinite sum of delta functions, so that it has a set of discrete frequencies, although the definition doesn't say that has to be all the spectrum it has. Speaking in a less formal way, we may say a quasicrystal is a distribution of discrete point masses whose Fourier transform is also a distribution of discrete point masses. Or to put it more briefly, a quasicrystal is a pure point distribution that has a pure point spectrum. This definition includes, as a special case, the ordinary crystals, which are exactly periodic distributions with exactly periodic point spectra. Excluding the ordinary crystals, quasicrystals in 3 dimensions come in very limited variety, all of them being associated with the icosahedral rotation group. The 2-dimensional quasicrystals are more numerous, roughly 1 distinct type associated with each regular polygon. The 2-dimensional quasicrystal with pentagonal symmetry is the famous Penrose tiling of the plane, discovered by Penrose before the general concept of quasicrystal was invented. So here's a picture of the Penrose tiling. You've probably all of you seen that many, many times. And this is the inflation scheme for generating the Penrose tiling by inflation. So the definition of that, a tiling is a division of Rn into a finite number of types of polyhedral cells, and a tiling is fractal, which is if a subset of its vertices forms a tiling with bigger tiles of the same k types, and there exists a matrix capital A with integer elements such that every bigger tile of type I is formed by sticking together a certain number capital Aij small tiles of type J. So we call capital A the inflation matrix of the tiling. And here you see the inflation scheme for the Penrose tiling. A big fat tile is made out of small tiles, and a big skinny tile is made out of small skinny tiles. So the tilings, the Penrose tiling has tiles that are rhombuses of two kinds, fat and skinny. All the angles are multiples of pi by pi over 5. And I think I won't bother to go through all this. The time is getting short. I might as well skip a good deal of this. Yes, so that's just details of the Penrose tiling. It's based on this quadratic equation which defines the golden ratio x squared equals x plus 1. Then Paul Steinhardt then invented a similar tiling for heptagonal symmetry. Here's a picture of Penrose's. This is Steinhardt's tiling with three kinds of rhombi, fat, medium, and skinny. And they fit together, and this is the inflation scheme for this sevenfold symmetry. So it's a quasicrystal with sevenfold symmetry of a heptagon. And so here are the roots of the eigenvalues of the inflation matrix are the roots of this cubic equation. X cubed is 2x squared plus x minus 1. But I think I'll skip most of the details of that. It's sort of irrelevant. The connection between quasicrystals and fractal tilings was found by Enrico Bombiri and Jean Taylor. And that's a theorem which is sort of nice. A fractal tiling with inflation matrix A is a quasicrystal if and only if the largest eigenvalue of the inflation matrix is a Piso number. And a Piso number is a positive real algebraic integer whose conjugates all lie inside the unit circle. The Piso numbers are, for those of you who are, it's like being an amateur astronomer. If you study the Piso numbers, you can fall in love with them. They have a wonderfully intricate topology. They are discrete. They're a discrete set of points on the line, which has all sorts of strange properties, which I will skip. The smallest Piso number is Carl Ludwig Siegel actually in his youth played around with Piso numbers. And he discovered the smallest Piso number is the root of x cubed equals x plus 1. And we don't know, the Salem numbers are those which are positive real algebraic integers with conjugates all inside or on the unit circle. It makes a huge difference if you allow them to be on the circle. So we don't even know what the smallest Salem number is, or even whether there is one. They may go all the way down to 1. But the smallest known is the root of this 10th order equation. Anyhow, I think I don't need to waste more time on that. I want to go to the main point, which is Riemann hypothesis. Finally, we get to the point. So we come to the punchline of the argument connecting one-dimensional quasicrystals with the Riemann hypothesis. If the Riemann hypothesis is true, the Fourier you start out by defining a set, which is just the set of the imaginary parts of the complex zeros of the zeta function. Call that capital Z. The set of, so this is just the zeta function zeros rotated so they lie on the real line. If the Riemann hypothesis is true, the Fourier transform of this set Z, the imaginary parts of the zeta function zeros, is also a sum of delta functions with coefficients 1 over k at all points plus or minus k log p, where p is a prime and k is a positive integer. So here's actually a picture. This is again calculated by Odlyzko. This is the actual Fourier transform of the zeta function zeros taken over some long stretch between 10 to the 20th plus 1 and 10 to the 20th plus 40,000. So that's about 100,000 zeros. So Odlyzko computed the zeros and took the Fourier transform, and here it is. And you see it just consists of these wonderful peaks at all the logarithms of the primes, except that it also includes the squares and the cubes and the fourth powers. So you see the value of 4, the value at 4 is less by a factor of 2, and then the value at 8 is less by a factor of 3. The value at 16 is less by a factor of 4. It's plotted on a logarithmic scale. And the value at 9 is less by a factor of 2. Otherwise, the peaks are all equal. And in case you're not convinced by that, here's a picture of how it looks further along. So here is another stretch of the Fourier transform of zeta function zeros. This is between roughly 3,000 to 3,120. And you see that it has all these beautiful peaks, all exactly equal at the primes, each of the primes between 3,000 and 3,121. And then, in addition, you have this peak at 3,125, which is the fifth power of 5, which is just a factor of 5 below all the others, since it's the fifth power of a prime instead of being a prime. So that is, again, a wonderful numerical demonstration that this is a quasicrystal. So if the Riemann hypothesis is true, the Fourier transform of Z, the zeros, is a sum of delta functions with coefficients 1 over k at all the points plus or minus k log p, where p is a prime and k is a positive integer. If the Riemann hypothesis is not true, then the Fourier transform of Z is a messy expression involving zeros off the critical line, and it's definitely not a sum of delta functions. Z does not qualify as a quasicrystal according to the official definition because it is not a Delaunay set. The zeta function zeros, of course, get closer and closer together as you go up the line. So it's not true that if you make a small circle, you don't find two of them together. But it is, this set Z does have the essential property of a quasicrystal, namely a discrete Fourier transform. So I take the liberty of generalizing the definition of a quasicrystal so that Z will qualify. So I say a generalized quasicrystal is a set of points which is 1 aperiodic, 2 locally finite, and 3 has points in every sphere of some radius r, and 4 has a discrete Fourier transform. Then, according to that definition, Z is a generalized quasicrystal if and only if the Riemann hypothesis is true. So my proposal is the following. Let's pretend we don't know that the Riemann hypothesis is true. Let's tackle the problem from the other end. Let's try to obtain a complete enumeration and classification of all one-dimensional quasicrystals. That is to say, we enumerate and classify all point distributions that have a discrete point spectrum. We shall then find the well-known quasicrystals associated with piezo numbers and also a whole slew of other quasicrystals, known and unknown. Among the slew of other quasicrystals, we should be able to identify one corresponding to the Riemann Zeta-Function and one corresponding to each of the other zeta functions, L functions, that resemble the Riemann Zeta-Function. Suppose we can prove rigorously that one of the quasicrystals in our enumeration has properties that identify it with the zeros of the Riemann function. Then we have proved the Riemann hypothesis and can wait for the telephone call announcing the award of the Fields Medal. So I propose as an exercise for students the following simple task. Classify all one-dimensional generalized quasicrystals and make a list of them. After you've done this, look at the list and see whether Z is there. These are, of course, idle dreams. The problem of classifying one-dimensional quasicrystals is probably horrendously difficult, probably at least as difficult as the problems that Andrew Wiles took 7 years to fight his way through. But still, the history of mathematics is a history of horrendously difficult problems solved by young people who were too ignorant to know that they were impossible. The classification of quasicrystals is a worthy goal and might even turn out to be achievable. Problems of that degree of difficulty will not be solved by old people like me. So let the young people now have a try. Thank you.
Thank you for such a wonderful lecture. Are there questions?
So it doesn't have to be about this. Questions about anything will do. How do I
Is there any hope of your writing up or making available the work that you reported earlier about spurious signals in levels?
I suppose one could. It's not very complicated. If there's sufficient demand, I might do that. I haven't been in touch with Henry Kamada for about 30 years. So it would be interesting to get together on this. Yes.
Why should one think that any one matrix exists whose statistics and eigenvalues coincides with the average over all the ensemble?
Well, you don't have to believe that, but it's a possibility. We know that the eigenvalues have these correlation functions, which is just what they should have if they were a random matrix. So possibly maybe it is a random matrix. We don't know. Certainly, you don't have to believe it. Yes.
Have you ever seen a reasonable probability measure on quasicrystals?
Have I what?
A probability measure on
Probability measure? I don't know. So little is known about the ensemble of quasicrystals. I mean, we don't. So I don't know how you define a measure on something you don't understand.